All right, here we go. So we're going to learn about some pulleys. This is honestly not too different from what we did in the last section. The big thing is that you need to remember that the pulleys are going to change the direction of your force. There is one new thing here, though, that's going to come up that you will not have seen before. All right, so, but let me remind you real fast. So in the last video, we talked a little bit about tension. We had this idea here that, if the rope is pulling the hand this way, then the rope is pulling the block this way. And so your tension forces, in most ordinary circumstances, directly oppose each other, right? But a pulley serves to bend that, right? So here, the hand is being pulled up by the rope, but the block is being pulled forward by the rope, right? And similarly over here, the hand is being pulled up by the rope, and the block is being pulled up by the rope, okay? So your pulley kind of serves to change the direction of your tension force, okay? And so what that does is it makes the fact that this is linear motion a little bit more complicated, right? Because in this situation here, look, there are two different directions that our system can go, right? We've got, one block here. We've got two blocks over here. There are two possible directions the system could go. In this example, it's fairly clear that it's going to move in the direction of the heavier block, right? So, all right, so I'm going to choose to make this direction positive and this direction negative and solve it with that convention, okay? So, as usual, we're going to start with a free body diagram of the system. So, I guess I'll make a new drawing. So here's our thing, pulley. Over here we've got a block with mass M. We'll call that, we'll just refer to them by their masses, right? So we'll call this block 1, block 2, and block 4. Okay. Okay, and then over here we've got a total mass of 2 plus 4, so 6M, right? Okay, so over here, force of gravity on block 1 is just negative mg. Oops, I don't like that I made a capital G there. Let's make it a lowercase g. All right, and notice, right, it's encouraging direction in that, or motion in that direction, so I had to make it negative. Over here, the force of gravity on blocks 2 and 4 combined is going to be 6m times g, and that's in a positive direction, right? Okay, so now I can do net force equals net force. So for my system, net force equals net force. So mass times acceleration. So our total mass of the whole system is 7m. That equals 6mg minus mg, right? So you get 7m equals 5. Oh, man, I am struggling today. Sorry, I forgot my A. Let's rewind. Net force equals net force. So mass times acceleration equals, we got this mass here, plus negative mg, right? So we get 7m times A equals 5 mg. The m's cancel, and you get the A equals 5/7 g. Okay, so there's the acceleration of the system, all right? Notice it's in a positive direction, which is exactly what you would think, right? Because there's more force that way, more weight on that side, I guess, is probably a sloppy way to say it. All right, so now let's go back and find the tensions, all right? So, let's start with block 1. Block 1 is a little bit simpler, right? Because there's only two forces on it. I guess that's, yeah. All right, so here we go. Force of gravity on block 1 is just negative mg. I'm going to stick with this being negative and this being positive. And then there's a tension force, which is what we need to find. Let's call that tension. Let's call this rope here, we'll call this rope number 1. And we'll call this rope in here rope number 2. So this is the force of tension in rope number 1. All right, and so once again, I'm just going to do net force equals net force. So for block 1, net force equals net force. So the mass of block 1 times the acceleration, oh, that's 5/7 g, equals the force of gravity, which is negative mg, plus whatever my tension force is, right? So add mg to both sides, and you get 12/7 mg is the tension. Okay. So All right, and then to find the tension in the other rope, you basically repeat the process. Why am I having such a tough time making this video? All right, so here we go. So here's this guy, right? So it's got a mass of 4m. Pretend that's a capital M. All right, and I need to find the force of tension number 2 here, right? So the other force is our gravity, which is 4mg. Again, pretend that's a capital M. Now we got to decide on directions here. Because there's nothing sort of bending my forces, I'm going to revert back to making down negative and up positive. But that does mean that we need to be careful because my acceleration then is going to be negative 5/7 g, right? Okay. Now, if you prefer to make up negative and down positive, then you don't need to worry about it. But the point is, you have to stop and think about your signs. Okay. All right. So, looking now at block number 4. Sorry, that's not what I wanted to do. We can do net force equals net force. So 4m, capital M, times my new acceleration of negative 5/7 g equals my force of gravity plus my tension. Let's solve it. So this is what, negative 20 over 7 mg equals negative 28 over 7 mg, right? 4 is the same as 28 over 7. Plus the tension, so add, and you get 8/7 mg equals the tension force there. All right. And then finally, if I wasn't recording a video, I would take a minute and check to make sure that works out. Well, you know, let's do it. I have time. I don't know if you have time. All right, so let's see. So what's that block going to look like? Well, let's see. There's our mass. Fg is negative 2 mg. There's a tension force from rope number 2. Oops. Tension force from rope number 2, which is negative 8/7 mg. And there's an upwards tension from tension number 1, which we discovered to be 12/7 mg. So find your net force, divide, and get your acceleration. And you do end up getting negative 5/7 g again. Okay? So there you go. Yes. All right. All right. So this example number 2, I'm actually not going to do right now. But it was too good of an example to completely get rid of. So I'm going to leave it up here. The answers are here. This is probably good practice for you. It's basically just more with pulleys. The one extra thing is that there's friction in here. And so that complicates things a little bit. But I believe you guys can all do this. So give it a go. If you can't get the answers to work, then when I see you in class next time, holler at me and we'll go over it. Okay? All right, so example number 3. All right, so here we've got this system, and it tells us that it's in equilibrium. We need to find the tension in each rope in terms of M1 and G. So first of all, the words each rope is a little misleading because there's really only one rope here, right? So finding the tension in the rope ought to be easy, right? So which block do we want to look at first? Well, M2 is pretty simple. If this thing is in equilibrium, then the net force everywhere on each individual thing needs to be 0. So if we look at M2, here's what we know. It's got a mass of M2, which means that there's a force of gravity down here of negative M2G, and there's a tension force. That must be equal to positive M2G, right? Because otherwise, it wouldn't be in equilibrium. Okay? Now, if we look at M1, M1 is going to be pulled down with a downward force of negative M1G. But notice, the rope connects with M1 twice, right? Assuming that the pulley is massless, we can kind of treat all of this as one object. Okay, and so we've got a tension force here and a tension force here, and they're equal, right? And we already know that our tension force is M2G. And so now if my net force is 0, that means that M2G plus M2G minus M1G has to be 0. So we have 2 M2G equals M1G. Divide out by the G's, and your M1 is 2 times M2, or maybe more usefully, M2 is M1 over 2, right? So, there you go. And so then your tension, I guess, since it said to write it in terms of M1, is actually M1G over 2, right? Okay. So that is that. Now, here's what's new. This is the new thing in this video, and I will do an example of this. But what if it had not been in equilibrium? Okay. What if M2 was heavy enough to make M1 go down? Okay. So, you know, I mean, we could solve this like a system, but what I want to point out is this. Suppose M2 moves down. As M2 goes down, M1 is going to go up, right? And so your knee-jerk reaction is yes, and they're going to move with the same acceleration. But that turns out not to be the case. It turns out, not because of the masses here, but because of the way the pulleys are set up, it turns out that because, how do I want to say this? Because M1 is connected with the tension force twice, it turns out that it's going to end up with half of all of the linear values as M2. In other words, if object 2 goes through some displacement, then the displacement of object 1 is only going to be half as big. Okay? Similarly for velocity, if the velocity of object 1 at any given instant is going to be half the velocity of object 2 at any given instant. And the acceleration of object 1 is going to be half the acceleration of object 2, okay? And this isn't because of which object is heavier, it's because of the way the pulleys are laid out, okay? All right, so let me show you a little bit about what I mean, all right? And to do that, I'm going to jump over to here, to this thing, okay? So here we go again. We've got our M1 here, right? Oh, where's that M2? Yeah, that's M1, okay? So we've got our M1 here. All right, and then over here, we've just got this hand, which kind of, you know, corresponds with our M2, right? Okay, so what we're going to try to do here is we're going to try to lift this block up. We're going to try to lift this block up through this distance. Notice, 2 little hash marks, right? So we're going to lift the block up that distance, okay? And so to do that, we're going to pull this end of the rope down some distance, and I want you to watch how far we have to pull this end of the rope down to get this to go up this distance here, okay? So let me kind of clear up the drawing here, all right? And I'm going to go here and I'm going to increase my applied force. Oops. Increase my applied force. All right, and so what you can see is, I'll wait until it's done moving. Okay, so this distance here is showing us how far our sort of M2 went down, right? Look how far it went down. It went down, it looks like 1, 2, 3, 4 hash marks, right? So 0.4 meters. All right, and in return, this thing only went up 0.2 meters. All right, and the reason for that is this. As I pulled the rope down, this rope down through a distance of 0.4 meters, half of the 0.4 meters came from this side of the pulley, and the other half came from this side. And so the distance it went up is simply that. Okay? So, when you've got a pulley that sort of splits your tension force or doubles it, because you're doubling your force, you get half of the distance. Okay, I don't know why I'm having such a tough time explaining this. I'll do a demo in class that'll clarify this, all right? Okay, so anyway, this is a thing, okay? And again, it's because of the way the pulleys are set up. All right, so let's do an example. What we've got one here. Example 4 doesn't actually have the motion. I'm going to jump ahead to this last example, and then I'll come back and get example 4. All right, so here we go. So we've got this set up here. It says, assuming the surface is frictionless, find the acceleration of each block. Okay? So the idea is, this block is here, right? And there's going to be some amount of tension force pulling it forward, right? Okay? And that tension force is produced by these two ropes here, right? All right, and then over here, we've got a force of gravity of negative mg, right? So what we can't do this time, and this is, I think, the thing that's new, is we can't, so last year, every time we did one of these problems, we would start by looking at the system as a whole. And we can't do that this time because different components of the system have different accelerations, okay? So if block B accelerates this way at an acceleration of A, that's happening because block B is accelerating down with an acceleration of not A, but A over 2, right? Because since that tension connects twice, it's going to decrease your linear values, okay? So let's write a net force equals net force equation for both of my blocks, all right? So I'm going to do block A. So here we go. Net force on A equals the net force on A. So we're going to have mass times A over 2. Let's see. I think I want to make down negative and up positive, in which case I need to make this negative A over 2, right? Because it's going to accelerate down. And that's got to equal negative mg plus, I don't know how you want to write it. There's two tension forces, right? So I was debating whether I wanted to write plus ft or not. Okay, so that is one equation, all right? All right, so now let's look at block B. For block B, I guess everything is that way, so let's call this way positive, okay? Which is a little backwards from the way we usually do it, but since all of my forces and acceleration are that way, then I think we're good. All right, so if I do the net force on B is equal to the net force on B, then what we get is that the tension force, sorry, mass times acceleration. So our mass is 4m times our acceleration, which is positive A, equals my tension force, right? Okay. So I guess the thing here that is new is, one, we can't look at the system as a whole because they have different accelerations. And, in fact, the acceleration of object A is half the acceleration of object B. Okay, so now we can solve this mess. All right, so let's see. I'm going to substitute. I know Ft is equal to 4ma, so I'm going to replace Ft with 4ma. So that red equation then becomes negative ma over 2, right? That's this mess, equals negative mg plus 2 times this. And solve it. So let's see. First of all of the m's cancel out, right? And so I'm looking at negative a over 2 equals negative g plus 8a. So let's see, if I subtract, I'm going to get, let's do this, negative 8.5a equals negative g. Cancel out the negatives. A is g over 8.5. So there's our acceleration. Okay? And so now you could go back and find your tension just by plugging it in right here, right? So your tension is going to be 4 times 8.5 is what, 34m? Okay? so that is that. So, takeaway. If your objects have different accelerations, you can't start with the system. You have to look at the individual parts and solve these in a system of equations. All right, finally, let's go back and get this last example here. So it says, suppose the coefficients of static and kinetic friction between the boxes are 0.5 and 0.4 respectively. Assume the floor is frictionless. What's the maximum force which could be applied such that the system doesn't move? So if you can't see it, let me embiggen this. So if you can't see it, this angle here in here is 32 degrees, and you're applying some force F this way. All right, and the question is, what's the most force you can apply so that the system doesn't move? All right, and so hesitating a little bit here about how to solve this. All right, so I'm going to stick to the way I did it in my notes. If I can find my copy of them. Yes, good. All right, so in order to do this, we need to ensure that the net force on each piece is 0. And there's a couple of ways of doing this, all right? So let's start by looking at the 4 kilogram block. All right, so here's our 4 kilogram block. So you can start by putting in your force of gravity. It's going to be negative 39.2 newtons. Okay. This tension force is pulling this way, right? Okay. This force has some components to it, right? So there's an x component. So Fx is just going to be F times the cosine of 32, which gives you 0.848F. And notice negative, right? Because it's going to the left. All right. And then there's a y component, which is F times the sine of 32 degrees, which is, do I have it written down somewhere? No, I didn't write it down. I'm just going to write sine 32. Oh, here it is. 0.53F. Sorry, thank you for being patient. All right, and then finally there's a normal force, which is big enough to make everything here cancel out. So we would need a total of 39.2, but some of that is being taken care of by this vertical component. So there we go. So there's our free body diagram. Oh, no, it isn't. Because we don't want it to slide, right? So if the system was going to move, it would move this way, right? Which means that our static friction has to go this way to prevent the motion. And to maximize our force, we can maximize our static friction. So that's going to be our coefficient of static friction times our normal force. All right, so here we go. So if I simplify this, I end up getting this. My goal is I want no motion, right? So I need my horizontal net force to be 0, which means that all of this has to cancel all of this. So in English, we get this. We're going to get 0.848F. It's got to be big enough to cancel out my tension, or whatever that is, plus this mess. 0.5. You know what? If you distribute this out, I'm going to just do this. If you distribute, you end up getting 19.6 minus 0.265F. So let's just use that. Oh, yuck. 19.6 minus 0.265 F. T. No, just F. All right, so I guess we can simplify this, right? Add 0.265 to both sides. Does that give you a number that I've written down? It gives you a number, but I don't have it written down. Okay, well, we'll leave it like that. Okay, so that's that. So now, let's take a look at the other block. So if I look at the other block, it had a mass of 10 kilograms, right? Is that what that says? Nope, 14. Oh my gosh, I can't read my own thing. I guess it doesn't even really matter, actually, because here's the deal. What forces are on it? So it's got a mass of something. I can't read it, and it really doesn't matter. But because the only two forces on it are this, your tension force, and your force of kinetic friction, right? And that force of kinetic friction is going to be the same as this force of kinetic friction, right? Because this force of kinetic friction here is the bottom block dragging the top block backwards. And so because of Newton's third law, that means the top block is going to work against the motion of the bottom block, right? So this is the same thing I had before, specifically 19.6 minus 0.265F in the negative direction, right? Oh, this is big though, because now this tells me that in order to prevent the motion, I need this tension force to cancel this force out. Oh, so my tension force has to equal that kinetic friction. The tension force is equal to the kinetic friction, right? Oh. So I can go in here and replace my tension force with this. I guess get rid of the negative sign, right? Because we're just interested in the magnitude, right? So here we go. We get 0.848 F equals 19.6 minus 0.265 F plus 19.6 minus 0.265 F. And to get 0.848 F equals 39.2 minus 0.53 F. Add the 0.53 F to both sides, and you get 1.378 F equals 39.2, which means that F, after you divide by 1.378, is 28.4 newtons. Okay? So there you go. I think I'm done. We're going to have to talk about this one, I think. All right.